For my physics final project, I'll be looking at how catapults work and the physics behind them. So to do this, I built a rubber band powered catapult, and I looked at elastic potential energy, torque and rotational motion, projectile motion, and the effects of mass and air resistance. Okay, so let's start with the elastic potential energy of the catapult. So when the catapult arm is pulled back, the rubber band stretches, and by stretching the rubber band, it stores energy inside the material, and this stored energy is the elastic potential energy. So when you pull the rubber band back farther, more energy is stored inside the rubber band. So as a result, when you release the catapult, the object flies further because there is more stored elastic potential energy being transferred into kinetic energy through the projectile. So we can now put this to test. So when we put a paper ball inside of the catapult and pull the catapult back a certain distance, we see that the ball travels off screen. Now, if we do this test again, but instead of pulling the catapult back as far, this time we pull it back a shorter distance, so the rubber band is not being stretched as much. And this time you can see that the paper ball travels a much shorter distance. So this shows us that when the rubber band is not being stretched as far, less elastic potential energy is getting converted into kinetic energy, meaning that there's just a less elastic potential energy when the rubber band is not being stretched as far. Okay, so now we're going to talk about the torque and rotational motion of the catapult. So the catapult has an arm that rotates around a pivot, which is this straw on top of a skewer, and the rubber band applies a force to the arm, but this force is applied in the opposite direction of the pivot, which then creates a torque, and this torque allows the arm to rotate once the catapult is released, and as a result, this launches what is ever inside the catapult and makes that object become a projectile. So what happens when the catapult is being launched is the rubber band is pulled, which creates a torque, and as a result of this torque, the arm begins to rotate really fast, and whatever is inside the catapult then becomes a projectile as it is launched. And as you can see, once the object is launched, it goes through projectile motion. So as the paper ball leaves the catapult, the rubber band is no longer affecting it, and the only significant force acting on the paper ball is gravity. So gravity is pulling the paper ball downward as it continues moving towards the right with the kinetic energy it had just gained from the elastic potential energy. And this creates a parabolic curve, which you can see in slow motion. Okay, and finally, air resistance affects how far the object in the catapult will travel. Okay, so to test this out, I launched a ball with a low mass, and I launched a ball with a high mass. The ball with a low mass was just made out of a tissue, and the ball with a high mass was made out of paper and had a small weight inside of it. And here's the difference of the masses between the paper ball and the tissue ball. So air resistance is a force that opposes the motion of the projectiles as they're moving through the air. Basically how it works is as the projectile travels, air particles collide with it, and this acts sort of as a drag force. Okay, so now I put it to test, and I started with the heavier ball, and you can see this is where it lands. Now, when I put the lighter tissue ball inside the catapult, this is where it lands. It is a much shorter distance compared to the heavier ball. And because the heavier ball has a higher mass, it has more inertia, meaning it has a higher resistance to change. So the air resistance has less of an effect on the ball compared to the ball made out of a tissue.